G'day. Let me set the scene. It's February 1991. A missile has been launched with a military base in its sights. An anti-air defense system kicks into gear, ready to blow the enemy ballistic missile out of the sky, saving those living in the base. The system turns on, scans the sky for an incoming missile, looking at the part of the sky that sent it the trigger to activate. It looks and looks and looks and looks. A problem occurs. A floating point rounding error caused the internal clock to be off by 1/3 of a second. Under normal circumstances, such an inaccuracy might be unnoticeable. But when attempting to scan the sky for an object moving 5 times the speed of sound, the result was less than desirable. The system can't find anything and turns off, and the missile hits the base moments later. And less than 24 hours later, a software update was deployed to fix the bug that caused this issue. G'day everyone, I'm Joshua Carpeggiani. I'm a university student at the University of Melbourne, and I'm lucky enough to be working as a part-time software engineer at ANZ as a result of a Go project I did on decimal data types, which I'll be talking to you about today. And it's actually kind of a funny story about how I got going on this project. I met my now colleague, Julia, in a fruit and veg shop, and we started talking about software engineering. She mentioned that some jolly old fellow named Marcelo was trying to get some summer internship program going, implementing a decimal data type in Go. A couple of weeks go by, and some emails have been exchanged, and the project finally gets the go-ahead. And at this time, I was actually on the side of the road trying to hitchhike my way up from Melbourne to the Gold Coast. And I was checking my emails just to keep my sanity. And after this, I started going through a tour of Go to try to learn as much Go as I could to try to convince people that I knew what I was doing. Anyway, I got to the Gold Coast in the end and came back down to Melbourne and started working on my first proper software engineering job. And that's what I'm going to be talking to you about today. I'm going to be talking about floating point numbers, their pitfalls and their strengths, decimal numbers, which is the project that I've been working on, and which are possibly a better alternative, and the implications of using decimals. And to start with, I want to show a simple example, which is an example of the implications of using floating point numbers. And the simple example is we've got 3 numbers. We've got 0.1, 0.2, and 0.3. And so when we try to add them and we equate 0.1 plus 0.2 to 0.3, in normal everyday math, we'd expect these to be the same. But as you all know, when we do this, it evaluates to false. And when we look a little closer, we see that our value of 0.1 isn't 0.1 at all, the value of 0.2 isn't 0.2 at all, and our value of 0.3 isn't 0.3 at all. And to go a little further, I want to show an example of when this can become a massive problem. In this example, we're going to be simulating a clock over a period of 10 hours, and our units are going to be in seconds. So our time limit is going to be in 10 hours, and we're going to store the passing time in a float 32. And so for every second, we're going to iterate 10/10ths of a second and iterate our time counter 1/10 of a second, or 0.1, and then print the difference out in the end. And if we're counting in everyday math that makes sense, we'd expect the time that has passed to be equal to the time that has passed. But again, when we run this, what we find is that we have a problem. Our timer over the period of 10 hours is off by more than 41 seconds. And if you consider the speed of 5 times the speed of sound, that's enough to travel something like 71 kilometers in that time. And so why is this? Why do floating point numbers act this way? And the reason for that, as I like to say, is that not all numbering systems are created equal. And to kind of demonstrate this point, I want to go back to very, very basics and start talking about binary numbering systems. And so in the binary numbering system, we have two values. We've got 0 and 1. And so we've got our binary value of 1, which is decimal value of 1. We have our binary value of 1, decimal value of 1. And when we want to add more values, we need to add another place value. And when we do that, our decimal value goes up a power of 2, because we're counting in base 2. And we can do that again, and we have and now we have a value of 4. And in this very same way, we can go the other way and start counting in down powers of 2. And so we can have 2 to the negative 1, which is 0.5, and we can go down again, which is 0.25, 1 on 4, and then 1 on 8. And then the question comes up of how do we store these values? It would be very inefficient if we were to store a massive string of zeros followed by 1 digit. And so what we do is we invent the floating point number. So we try to move our point that is at the start of the number to somewhere where it is convenient for us to store. And in this case, we take the bit of information that we've got, which is a 1, and we kind of move or float the point to where it is more convenient to store. And thus, we have a floating point number. And then this is where the problem comes in, which is if we looked at the example before, we've only got inverse powers of 2 to play with. And so if we consider trying to get to a value of 0.1 in our decimal numbering system, we can estimate it with a value as 0.0001, which gives us a decimal value of 0.0625. We're not quite at 0.1 though. We can go a little further and add some more bits, and now we're at 0.09, and we're not quite there yet. So we can add some more bits and get even closer, but we're still not there. And then at some point, we need to chop the value. We've run out of bits of information that we can store, and we need to chop it, and we need to kind of round it in order to actually be able to represent it. And then when we do that, we actually overshoot our value, and so now we've gone above 0.1. And so this is the fundamental reason why we have those errors to begin with. And it's the same example as if we try to represent a value of 1 on 3 in our decimal numbering system. When we do this, we can estimate it with 0.3, we can get closer with 0.33, but the true value is 0.3 repeated. And so why is this? Why do our binary numbers do this? And the reason for this is that our binary numbering system, when we're thinking about discrete values and fixed precision, are in fact a subset of our decimal numbering system. And we can kind of explain this with when we take the factors of 10, which are 5 and 2, because 2 is a prime factor of our decimal numbering system. It means that we have a perfect representation for any inverse power of 2 that exists. But it doesn't go the other way around. And so the problem occurs when we have a value of 0.1 in this blue area, when we have a numbering system like our binary floats, which can only represent numbers in our red area, our binary numbering system. And so that's where I come in. I started working on this project around 10 months ago, and the idea was to have a numbering system which represented our blue area to avoid problems like this. And there were two real project goals. The first one was we wanted to implement a 64 and 128-bit floating point number. Other number libraries in Go already exist, but they're arbitrary precision, so they're slightly different, and also conform as closely to the IEEE standard as practical and as possible. And the standard we chose for a couple of reasons. The first one was because of speed. If we're conforming to a set standard we're using a 64-bit int or a 128-bit int, we're allowing for fast optimizations to be had, because if we're not using a big int, for example, we don't need to deal with any slices or pointers, for example. The second one is portability. If we're using a standard and everything means that it's portable, so we can give our data to other programs, and we don't have to have an intermediate typers and marshal it into a string, for example, and also extendability. And because we're using the largest decimal standard that exists, it also means that it gives way for future hardware optimizations. And so now we've kind of solved our problem. We have our value, 0.1, and we can take our value of 0.1 and kind of get the bit of information in our decimal numbering system, which is 1. We can multiply it by our base, and now that we're working in decimal, we have times 10 to the negative 1, and we have a value of 0.1 now, and there are no repeated fractions as we did before. And so now, if we go back to our first example, we can get our value of 0.1, we can add it to our value of 0.2, and then we can equate it to 0.3, and we get the expected outcome. And so for first example, we had this example, and now when we're looking at the code, we can pass our numbers in as strings so we don't lose precision in that step. We can use the add function to add them together and the compare function to compare them and make sure that everything is all right. But notice, unfortunately, Go doesn't have operator overloading, so we do need to use some wrapper functions in order to actually do the operations, which can be a bit tedious at times. If we take our second example, we have our clock. And so now, and when we run that, it becomes true. In our second example, we have our clock. And now, instead of using a floating point number, we have our time is a decimal 64. We have our increment as a decimal 64 set to a value of 0.1. And so now, when we run it, ta-da! I meant to, This was a backup slide, but I guess I needed it in the end, so it's fine. And so I'm not sure if the Gopher thing was going. Has everyone counted that? Okay, doesn't. All good? Okay, that's another one. Okay, I'm just going to keep. I'm sorry. I don't know how fast people count. It took me about 5 minutes to count those, and I made it, so I don't know. Anyway, so is that the end? Have we solved our problem now? And does this mean we can just use decimals for everything? And if not, why doesn't everyone use decimals for everything? Why do floating point numbers even exist? And then that begs the question of, are decimals even that fast? And it's interesting to note some research that IBM did before the decimal standard actually existed. And they did some research on some enterprise databases. And from a survey of a whole bunch of enterprise databases, they found that around 55% of all numeric data stored in enterprise databases was, in fact, of a decimal data type. And so this is a massive sector that needs to have a good application and a good a good library and good well-supported library and everything. And to explain this in a little bit more detail, I want to go through some specifics in decimal arithmetic. And for that, I want to list the example of this. So we have 9,999, and we add 1 to it. And what do we get? 10,000, of course. So we have 10,000. And now 10,000, this is a 5-digit number. And now if I pose the question, what do we do if we've only got 4 decimal digits to store this 5-decimal number? 5-digit number. And what we need to do is we need to shorten it down by using scientific notations, essentially. And so we do something like this. We take our number, we have it, we multiply it by our base, which is 10, and we need to think of the number of the exponent that we multiply it to. And intuitively, we know this to be 10 to the 1. And this is because, like, we all count in decimal, we all know how the decimal numbering system works. And so what we're doing in our head is we're doing 10,000 divided by 10. And we know, because we count in decimal, that we can just cross one of those zeros off. But the problem arises in computers because computers don't use a decimal numbering system to count. They use a binary numbering system. So they, in fact, need to do a binary computation. And so we've got the value of 10,000 here, and we have our value of 10, and we need to do integer division. You need to do some very long integer division here. And then we get our answer of 1,000. And if you can note something, which is if we take our value of 10,000 and you kind of look at the bits of that and compare it to the value of our 1,000, the bits are slightly off. They're not exactly as we'd expect it, like we would take the 1,000 in decimal, we've just removed a 0. But this bit pattern is fundamentally different. And so if we were to take our binary alternative to this, and let's say that we kind of pose the same problem, we have our binary value of 10,000, and we want to shorten it down to the least amount of space possible. And what we can do, which is really nifty, is because we're counting in binary now, and like we do, we just cross a 0 off, we can basically just cross all those zeros off at the end, and we can count that there are 4 zeros. And computers have a very good way of doing this, and the way of doing this is a simple bit shift, which is a very fast operation. And so we've shifted it 4 bits, and now we can, to expand it back out, we can simply multiply it by 2 to the 4, which is the amount of bits that we've shifted it, or even just bit shift it back the other way. And the fundamental thing is that bit shifts are much, much quicker than binary integer division. And so integer division, on average, takes 30 to 40 clock cycles to complete, whereas if you take a bit shift, it takes only 2 or 3, which is profound. And so this brings up the question of, now that we're trying to do decimal arithmetic in a computer that fundamentally supports binary arithmetic, how much slower is it? And so I did some benchmarks, and this was the result. And you can see, it's not great. And to begin with, I thought this was wrong. I thought I'd messed something up completely, but I rechecked it. I went on Dave Cheney's blog a whole bunch, and I reread the blog, and I reread it again, and it turns out I did it fine. This is correct, but it's just not fair. And the reason for that is that, like, if you know anything about floating point, like hardware and everything, the floating point computation is done in the floating point unit of the CPU. And so this is all the logic in that is done in the hardware. Whereas in our decimal numbering system, in our decimal library, everything, all of the code and the logic is programmed in Go, and then it's compiled down. And so a more fair approximation of this would be instead to use the software floating point number, which Go does. It's just a little matter of actually getting a type, which is a software floating point number in Go. But when we benchmark a software float, we get this. And so that's a lot better. And I was kind of pleased with myself when I found this out. And it's still around 7 times faster, but a couple of things to note. This library hasn't been fully optimized. Like I said, it is my first Go project, so I'm still figuring a lot of things out. And for the reasons we described before, which is if we're using binary operations in a computer and everything, using a binary numbering system is always going to be faster. And so then we kind of get to this idea, which is that maybe not all implementations of numbering systems are created equal. And to demonstrate this, I want to show a very simple function, which is a simple function of an add, floating point add function. And so we're just wrapping the normal, so we're taking 2 floats, we're adding them, and we're returning the value. And using the Go compiler, we can compile it down to machine code and get back the resulting assembler, and we get something that looks like this. And personally, I don't know anything about assembler, but there is one thing that I want to draw your attention to, which is this on line 10. If we look at this, add SD, that's the function that's called, and this is the singular function that does all of the logic and all of the arithmetic for our 2 floats. And so this is very, very fast, and this basically handballs it off to the floating point unit and then simply receives a result back, and then we can just return that. Whereas if we look at our decimal arithmetic, it looks something like this. So you see that we need to unpack it, we need to check if it's a nan, we need to check if it's infinity, and then we need to do a whole bunch of other stuff. And so you can probably tell what this is going to be like when we compile it and get our assembler code back. It looks something like this. We've got first, but it goes on, and it kind of goes on again, and it goes on more, and you get the point at this point. And it's crazy, to me at least, to think that of the IBM research that was done, to consider that 55% of decimal arithmetic is done this way in like enterprise servers at least. And just consider that inefficiency. And so we kind of get to this idea that maybe like decimal arithmetic at the moment isn't that fast. And there is a whole historic reason to why we use binary floating point units instead of decimal floating point units. And basically, the binary floating point units were at one point much cheaper to manufacture than decimal floating point units, and so that was the obvious choice. And so this begs a question, which is there a better way? Can we get, if we take the example of our clock, can we get our accuracy with our decimals, but still our speed and efficiency with our floating point units? And so for this very specific example, we can kind of rethink the problem. We can take our time limit, which is, and do everything the same, but in this, instead of using a decimal or a floating point, we can just use ints, and we can simply increment our time variable up one increment, and now one increment of our time unit is going to be equal to 1/10 of a second. And then, when we run this, we get the expected result. And obviously, this is a very specific example. If you're trying to do any sort of fractional calculation or something, or it's for some reason you need to change your base unit, this whole thing fundamentally falls apart. It's very difficult to do, which is why floating point units and floating point calculation was invented to start with. And so we kind of get to this conclusion, that you should use floats if you really need performance but not precision. You can use ints as your smallest unit if you can rethink the problem and you're sure that you're never going to need to change your base unit again, and use decimals for everything else. And with that being said, if you want to come and contribute at github.com/ANZbank/decimal, you should come and help out if you're interested in any of this stuff. And also with that being said, there's there is another library, which is Eric Lagergren /decimal, really good arbitrary precision, so it doesn't pack it into 64 bits or 128 bits. And looking forward, what this project needs is obviously more optimization, as we saw before. Implement a 120-bit decimal. That's proved to be difficult at the moment, seeing that we all know that working with 128 bits in Go is quite pleasing. And so it kind of, and also assemble optimizations so we can make it faster for different architectures. And I know it's a very debated thing about what goes into the Go core and everything. And I know every man and his dog wants to put something in the Go core, but over the years, there have been a number of proposals to get a decimal data type in the Go core. And these reasons stem from intuitiveness and seeing that we count in a decimal numbering system. Maybe we should have a type that supports that thinking, and especially from a programming language like Go, which boasts readiness out of the box. And just take, for example, the 55% of enterprise databases which store their numeric types as decimals. And other arguments stem from other number types. And one of them is Go already has a complex type, and how often do people actually use complex types? And so obviously a decimal type would be used more than that. And so with that being said, there is actually an open proposal which was proposed in 2017, and it hasn't been closed. And so it is a point of contention, but then again, maybe not. Maybe decimals just aren't quick enough, and because they don't have hardware support, they're not up to scratch for the Go core. And yeah, that's me. Thank you very much.